Good morning, chemistry team. Your chemistry coach is coming at you for video number 13. This is a long chapter of thermodynamics, but this is it, gang. This is the end of the journey for thermodynamics before we get into electrochemistry. A lot of overlap. All right. What we're going to do is there's really nothing new here. We're just going to apply concepts we already know. Remember Hess's law. And we're going to do some cool stuff with that, right? That's what chemists like to do. Understand nature, manipulate things around, manufacture it, get into industry, all that fun stuff. So coupled reactions. Coupling means putting together, obviously, or adding equations together. Can you sense Hess's law from this? So what if we run into a scenario? We did this with enthalpy of reactions. We're going to do the same thing with Gibbs energy of reactions. What if we have a non-spontaneous equation or reaction? So it's not going to happen on its own. It needs some outside help. It's got a positive delta G overall. Could be a standard conditions or non-standard conditions. Doesn't matter. What do? What if we are running an industry, or manufacturing something we want to sell? Or what if it's a biochemical process? Maybe you run into this in physiology. How do we make that spontaneous? Nature's quite fascinating, and industrial chemists are quite brilliant in how they have approached these things, especially extracting, metals from their ores, trying to make those profitable, making, or your body trying to make some kind of reaction that's necessary for life to happen, but it needs to couple it with another one. So two options here. One, which we've already looked at in prior videos, change the temperature. Remember that video where we had a non-spontaneous reaction? And based on delta S versus delta H, you could increase the temperature. And then there's that inflection point where it goes from non-spontaneous to spontaneous. We could do that. Kind of hard to do in your body. You might die if you try that, right? So you don't want to be changing the temperature for a physiological process. But in industry, hey, if you got the money and you want to spend it, increase your overhead for some extra heat to jack up the temperature, maybe it's a profitable venture. Who knows? That's not my forte. But what we could do, this is what nature does, amazingly so. They couple that non-spontaneous equation with one or more other equations that happen to be spontaneous. So if you take an equation of interest that's not spontaneous and add it to one that is spontaneous, and the negative delta G of the spontaneous one is greater than the positive delta G of the non-spontaneous one, you add those together, the overall total happens to be negative, which would make the overall reaction spontaneous. Oh, isn't that neat? And of course, we can use Hess's law when we're trying to get from one state to another. You can do it by multiple paths, so we can do that directly or combine 2, 3, 4 different equations together to get to the same equation. So we can use Hess's law to put those things together, which we did back in Chem 180 with enthalpies of reaction. So nothing really new here. We're just adding the term coupling, right? Just adding them together. So it's probably been a while since we've dealt with Hess's law for thermodynamic stuff and adding equations together, manipulating equations. So we'll review manipulating thermodynamic equations. We did it for equilibrium, but the rules are different. Remember with equilibria, for you reverse an equation or multiply it by 2 or divide it by 3 or something, the overall K value changed of that. The same thing's true with thermodynamics, but the mathematical rules are a little different. So let's review that real quick. Maybe do a sample problem to get the rust out of the brain, and then we'll show you how to couple some reactions together. Be right back. All right, a little review for you here. It should be nothing new. The only difference is we're going to apply it to Gibbs energy changes rather than enthalpy changes for reactions. All right, here we go. When we are playing the manipulation game, you should have got really good at this. Probably introduced in last semester, in first semester of general chemistry. And then we did it a lot in equilibrium. But again, like I said, the rules are different, and I'll compare and contrast them here. In thermodynamics, or thermochemistry in first semester, here's the rules. When we are adding 2 or more equations together, right, using Hess's law to do that, the overall delta G reaction for that overall equation is the sum, it's additive. It will be the delta G for the first reaction plus the delta G for the second reaction plus the delta G for the third, and on and on and on and on. However many equations you are combining, you're going to add those together. That was different in the equilibrium world, right? In equilibrium, when you added a bunch of equations together, you multiplied the equilibrium constants together. Ooh, a little different. Don't get those confused, right? In equilibrium, you multiply them. In thermodynamics, you add them. This could also be delta H's as well, any state function. All right. If we're going to manipulate things, so let's say I give you 3 equations and say, hey, add these together and manipulate them to get this overall equation. You might have to reverse a few, multiply a few by 2 or 3 or 1/2 like we've done before. But if we reverse an equation in thermodynamics, remember the first law of thermodynamics, I mean, the energy is the same, right? The numerical value is the same. It's just going from one way to another. Think system to surroundings, those kinds of things, right? So if I have an equation in the forward direction with a positive value of delta G, the reverse reaction is the exact same numerical value. It's just negative. That's it. It's just going the other direction. So if you reverse an equation, the sign on delta G is reversed. All right, that's all it is. That was different in equilibrium, right? In equilibrium, when you reversed it, when you reversed an equation, you inversed the equilibrium constant. You did 1/k. Oh, why do they have to change the rules? All right, number 3. If you have to manipulate an equation by multiplying it because the coefficients are wrong, right? When you add the equations, the coefficients don't work up. So maybe you have to multiply an equation by 2 or 1/4 or whatever, some numerical value n. Okay? So when I multiply an equation by some factor n, which could be anything, the delta G for that reaction is also multiplied by that exact same factor. So if I multiply an equation by 2, I have to multiply the delta G by 2 because delta G's in thermodynamics are extensive properties. They depend on how much of the substance there is. That was different for equilibrium. For equilibrium, if we multiplied an equation by 2, you squared the equilibrium constant. If you multiplied it by 3, you cubed it, right? You raised the k to the power of that factor. Here you don't do it. You multiply it by the power of that factor. Oh, how are we going to keep all this together? Good thing I separate these on the 2 different tests, so you don't have the same rules on one exam. So let's do one example just to see if you remember how to do this. All right, get your thinking caps out, or if you need to go review your notes from thermochemistry from first semester general chemistry, you might want to do that. All right, here we go. What is delta G naught? It happens to be at standard conditions in this scenario at 25 degrees Celsius for the following reaction. 1 mole of solid sulfur plus 1 mole of oxygen gas, diatomic oxygen gas, giving us 1 mole of sulfur dioxide gas. Seems pretty simple. But let's say we don't have the data to calculate that. We got to do it a different way. So we find 2 equations that we can manipulate and add together to get that overall equation. Right? So you got to play with it a little bit. You got to think. It's like a game, like a logic problem. And we find that the Gibbs energy change of standard conditions for equation 1 is a negative 141.8 kilojoules per mole. And that for equation 2, the Gibbs free energy change of standard conditions happens to be negative 371.1 kilojoules per mole. Because these are standard conditions at 25, I actually just calculated those using the thermodynamic tables in the back of your book. Right? So you could do that as well. That would be a long problem. I could, on a test, theoretically say, well, look up the delta G values. I could give you an equation that you couldn't do using that table, giving you 2 equations you could use that table for. So you could have calculated those, right? Look on your chart. You can see where those numbers come from. Just to the products times their coefficients minus the reactants times their coefficients. Works out nicely. So what we got to do is manipulate these. Do we got to reverse these equations? Do we have to multiply them by 3 or 4 or 1/2 or 1/3 or 9.7 times 10 to the 50? No, that's not going to happen. Let's think about this a little bit. Take a look at the equation of interest. This is what we're after. So I need to get 1 mole of solid sulfur on the left-hand side. Okay, let's look at the 2 equations I gave you. The first one is 2 moles of sulfur dioxide gas plus 1 mole of diatomic oxygen gas, giving me 2 moles of sulfur trioxide gas. I don't see any solid sulfur in there, do you? Wow, so that's not going to help us. Let's look at the second one. The second one provided is 1 mole of sulfur on the left-hand side plus 3/2 a mole of oxygen gas, giving us 1 mole of sulfur trioxide. Well, that has solid sulfur. Do you see that? And it's on the reactant side, which is what we want, and it's the correct coefficient. So I'm going to leave equation 2 alone. It has the solid sulfur. I'm always looking for a species here that's in only one of the reactions provided. Then I can play with it. If it's in both of them, like the oxygen, that's too hard. Hopefully that'll work out in the end. So this is the plan. We are going to leave equation 2 alone, because I want 1 mole of solid sulfur on the left-hand side. All right, now you see we need 1 mole of oxygen, diatomic oxygen on the left-hand side, but both equations contain oxygen, so heck with that. That ain't gonna happen. That's too hard. It's like one equation with 2 unknowns. Good luck with that one. I need 1 mole of sulfur dioxide gas on the right-hand side, on the product side. Okay, so what has sulfur dioxide? Oh, the first equation does. Does the second one? It does not. Oh, I can work with that. I need 1 mole of sulfur dioxide on the right, but the equation 1 gives us 2 moles on the left. Well, I need to move the SO2 over to the other side. I need to reverse equation 1 to get the sulfur dioxide on the right-hand side. So what I'm going to do is I'm going to reverse equation 1 to get the sulfur dioxide, but that would give me 2 sulfur dioxides on the right-hand side. I only want 1. So I also have to multiply it by, wait for it, 1/2. I need to multiply it by 1/2 because 2 times 1/2 is 1. So what I'm going to do is I'm going to add these two together. I'm going to manipulate these, write the new equations, add them together, and I should get that overall equation, correct? When I add them together, the overall delta G will be delta G1 plus delta G2. Delta G2 will stay the same, but delta G1, I'm going to have to change the sign, because I reversed it, and multiply it by 1/2. So it's going to be that times negative 1/2, and then I can add those together. See if you can do that before I do. Give it a shot. So I'm going to write on a new board these new equations. I'm going to reverse 1 and multiply it by 1/2. I'm going to leave 2 the same, write those, and then I'm going to add them together, cancel out like species on either side. I better end up with that overall equation. If you don't end up with that overall equation, something went wrong. All right, guys, hopefully you did it. I rewrote equation 1 and 2 after manipulation. So equation 1, we reversed it. So the SO3 that was on the right is now on the left. The SO2 and oxygen that was on the left are now on the right. I multiplied everything by 1/2. So 2 times 1/2 left me with 1. 2 times 1/2 left me with 1. And 1 times 1/2 left me with 1/2. That's why I'm taking the original delta G1 value times negative 1/2, because I reversed it. That's why the negative sign's there. That's the rules for thermodynamics. And I times it by 1/2. Because I multiply it by 1/2. That's the rules for thermodynamics. Very different from equilibrium. Equation 2, I didn't manipulate at all. I left it exactly like it was. So I leave it as the sulfur plus 3/2 moles of oxygen, giving me the sulfur trioxide, and I leave the delta G as the original delta G2, equation 2 that was provided. So take everything on the left-hand side. So I'm going to take the 1 mole of SO3 gas plus 1 mole of solid sulfur plus 3/2 moles of oxygen gas, all on the left-hand side, reactant side. And then I take everything on the product side, 1 mole of sulfur dioxide gas, 1/2 mole of oxygen gas, and 1 mole of sulfur trioxide gas. So everything on the left, everything on the right. Let's look for things that are the same. Do you see the sulfur trioxide? I have 1 mole of sulfur trioxide both on the left and the right. So that's going to go bye-bye. I don't have solid sulfur on the right-hand side, so that doesn't cancel out. I do have oxygen on both sides. I have 3/2 of a mole on the left and 1/2. So if I subtract 1/2 a mole, that will go to 0. And that will go to, subtract 1/2 goes to 1. 3/2 minus 1/2 is 2/2. 2 divided by 2 is 1. So that'll leave us with 1 mole of oxygen. And then the sulfur dioxide does not cancel out. So our overall equation will be solid sulfur, because that's left. The SO3 is gone, plus 1 mole of oxygen gas, giving us 1 mole of sulfur dioxide. The 1/2 mole of oxygen's gone, the sulfur trioxide's gone, and that matches the original equation provided. Always do that. Always do the overall and make sure it matches, because if it doesn't, you know you're off. Well, from Hess's law in thermodynamics, we know when we add equations together, we add the delta G's. So delta G overall will just be those two added together. So it's going to be negative 1/2 of the original delta G given in 1 plus the original delta G2, because we did not manipulate that equation. Hey, so let's do that. Let's take negative 1/2. Ooh, that's a pretty ugly 1/2. Times the original delta G1. What was that? Negative 141.8 kilojoules per mole. Let's add the original delta G2, negative 371.1 kilojoules per mole. And since this is an exact number, this is essentially an addition problem, so we're limited to 1 decimal point. 1 decimal point. If I'm out of room, no, I would normally just multiply those together to take half of that, right? To give me, what would that be? Positive 70.9 kilojoules per mole. So I would add another step and go 70.9 kilojoules per mole plus negative 371.1 kilojoules per mole, and then give me the final answer. But I don't have enough room on the board, but you see those negative signs cancel out. So the net effect, I get negative 300.2, good to 1 decimal point, kilojoules per mole. So that would be the delta G at standard conditions at 25 degrees Celsius for this reaction, utilizing delta G's of other reactions that were manipulated. The only thing different last semester is we used delta H values. Okay, the rules were the same. So let's look at how we couple these together. Something simple, just to give you an idea. It's the same process, so I won't do something as complicated. Let's just do maybe 2 reactions, pop and add them together. I won't make you manipulate much. It'll be pretty simple. All right, this will make some of you biochemistry and physiology medical people happy. Not me. But anyway, 2 of the most important things that, again, I see coupling reactions provided to is in industry. Like I said, extracting metals from their ores and whatnot, because it takes a lot of energy to do that. So sometimes they couple them. You can look up into, I had one of my best friends, Price man, good to see you, worked at a place where they would make they would have this molten steel or molten iron. Don't understand the process super well, but they have a blast furnace and you can create pig iron and all this kind of interesting stuff. And he actually got some of that on his back and burned his back. Ouch! Right, molten steel or iron, pretty crazy. But I think they use Coke or something like that. Not Coke like you're thinking of Coke, like Coke or that kind of Coke, but like solid carbon. And they can burn that and couple that with other reactions to make the overall process profitable, right? Interesting stuff. Same thing with physiology, biochemistry. This is just a typical example. We want ATP for energy, right? But once we use it up, it loses some phosphate groups, so we need to put those back on. That requires energy. So if we take ADP and tack on a phosphate with it, and of course, and we tend to use H3O plus in chemistry, but in biochemistry, it's not that critical. They just oversimplify it with an H plus to get ATP plus water. All right, and of course, leaving the states off. Just we're going full bio here. To do that, to pop that on, is not spontaneous. All right, that's 32.4 kilojoules per mole. It's not going to happen. It's positive. But the body's quite creative. So what it does is it couples it with a process called glycolysis. Right? We're taking glucose or sugar and breaking that down for energy. And that's where the energy is going to come from. So if we couple these two together, the overall process should work out. So take your glucose, produce 2 lactate ions plus 2 H pluses there. If we add these, if we manipulate these and add these 2 equations together, notice that the first one of interest in creating the ATP is not favorable. That's not spontaneous. But the glycolysis is, the breaking down of the glucose, that's negative 218 kilojoules per mole. That's spontaneous. So let's add these 2 equations and cancel out the H pluses and see what we get for our overall delta G. And if that is negative, then we can couple these together and your body can make that happen by doing this simultaneously. Pretty cool. So think about what we're going to do. I want to get rid of the H plus. Now the ADP and the glucose, we don't have to reverse anything, right? Everything's on the correct sides. The H pluses are on opposite sides, but we got 2 moles here, right? So if we multiply that first equation by 2, let's multiply that by 2. So we're manipulating, right? So multiply equation 1 by 2 and leave equation 2 alone. So we'll end up having 2 here, 2 here, 2 here, 2 here, 2 here. That 2 is going to cancel out that 2. And we'll be good to go. Go ahead and do that for me and calculate the overall delta G. All right, let's polish this baby off. Did you get what I got? This is a little easier than the first one, I think. All right, so I manipulated the equations. I took the first equation, no reversing, right? We just multiplied it by 2, so I get 2 of the ADPs plus 2 of the hydrogen phosphates plus 2 of the H pluses, giving me 2 ATPs plus 2 waters. Just multiplied everything by 2 across the board, which means, of course, we're going to multiply that delta G value by 2. It's an extensive property. Welcome to thermodynamics. Equation 2 we just left alone, so the delta G for that will just be the original delta G for the second equation that was provided. Remember, that first one was non-spontaneous, had a positive delta G. Second one was spontaneous with a negative delta G, and our goal is to add these together so that we have an overall equation with a negative delta G that is spontaneous. All right, let's add all these together. I'm skipping the intermediate here, but notice we have 2 H pluses on the left-hand side and 2 H pluses on the right. Those are going to cancel out. We're going to get 2 ADPs on the left plus 2 hydrogen phosphates plus the glucose. That's it there. The H plus cancels out. And on the right-hand side, we're going to have the 2 ATPs, 2 of the lactate ions plus 2 waters. The 2 H pluses cancels out. There's our overall equation. So the overall delta G will just be the sum of this one plus that one. Well, this one is 2 times the original delta G. So I'm going to take 2 times the 32.4 kilojoules per mole. That was provided for the original equation 1 before we multiplied it by 2. And then I'm going to add the original delta G2, which was negative 218 kilojoules per mole. Essentially, it's an addition problem. This is good to the ones place. This is good to the tens place. So we're only good to the ones place on this one. So I get negative 153.20 kilojoules per mole, closer to 153 to 154. So it rounds down negative 153 kilojoules per mole, which is spontaneous. The body is a miraculous thing on how it does this fun stuff. So, of course, we need our sugar, drinking our soda pops and eating our Twinkies and our Cinnabons. Yay! Life is good. However you get that, it works out fantastic. So that's the essence of coupling reactions. It's just a fancy way of just saying add a bunch of ones together so that the overall is what you want. Little good review there for you. That's it for our thermodynamics journey. Hallelujah! We are done! On to electrochemistry, my friends.